Hello everyone, my name is Matthew Moore. Welcome to my APS talk. So this is work that I have done in collaboration with Dominic, Vella and James Oliver. We're all at the Mathematical Institute in Oxford in the UK. And this is work on the nascent coffee ring, how solute diffusion counters advection. Hope you enjoy it. Okay, so first of all, we're going to talk about what the coffee ring effect is. So for most of this talk, I'm going to be talking as if this only happens for coffee, but that's completely not true. It happens more universally. So please excuse me if I just use coffee quite a lot as my example. So this is a video that I have borrowed from Kim and Weon's work from a couple of years ago, where they looked at the evaporation of various different types of commercial coffees. And I'm going to play the video and we're going to see what happens as it evaporates. So you can see early on not much is obvious, but as the droplet dries out, you can see the droplet radius doesn't change at all, and that towards the end of the drying process you get this band of brown colour around the edge, which is called the coffee ring. So you'll be familiar with this if you've ever spilt your tea or coffee on a table. So what's going on here? So I'm going to talk about ideas that were first established by Deegan and co-workers in the early 2000s. Late 1990s, early 2000s. So the idea is that we have this picture of I'm going to take an axisymmetric droplet. It's got a radius r star, which doesn't change throughout the evaporation process, so that once evaporation begins and the droplet starts drying out, conservation of mass drives an advective flow towards the contact line. And this drags along the particles with it. So the idea is that the particles are just carried with the flow at this point in the problem. So as it evaporates further, we get more and more in the contact line, so eventually they start to stick together and effectively jam near the contact line, so that more particles are deposited a little bit sooner. So that by the time the whole thing has dried out, we're left with this circular band around the contact line, which is called the coffee ring. So these jamming ideas were established by Popov a few years later. So to sort of summarize what's going on, we have this radial flow due to evaporation, the solute is carried along towards the contact line where the concentration builds up. Eventually it jams and you get this ring growing back into the droplet, which is great. So what's missing from the picture? So currently what's missing from the picture is that we have this sort of jump from just an advection problem to a jamming problem when we're depositing sooner. At some level, when the concentration increases locally, we must still be in a dilute regime, but the concentration is increased so much that diffusion comes into play before jamming. And so in this talk, I'm going to talk about when this effect is valid, so when diffusion is important before jamming, and how long the dilute regime can be assumed to hold because of this. So this is sort of why we call it a nascent coffee ring in this problem. We're actually just still looking at the dilute problem. Anyway, so this is sort of a schematic of what we're going to look at, and it has these sort of advective and diffusive fluxes. So this is what I was talking about. This is the flux that carries particles to the contact line, and eventually there's a countering diffusive flux here, which tries to push particles back away. And we're going to see what happens in our model. So there are some properties of the solute and the liquid there, and the sort of four key things that we're interested in are the droplet profile, the velocity and pressure within the drop, and most importantly, we want to know what the solute concentration, or sort of the profile of the coffee particles within the drop is, so we can see what's happening. Okay, so initially we're going to take these sort of simple assumptions. We're going to assume that the coffee is uniformly distributed in the drop and that we have a spherical cap. These could be relaxed, but we'll just concentrate on those here. And we're going to make four key assumptions. So the first is that we're going to assume the droplet is thin. So the droplet contact line is pinned, and we're talking about microliters worth of liquid here. So naturally the droplet's going to be quite slender, and especially as it evaporates, that slenderness is only going to become more stark. So we're going to assume thinness of the droplet. We're going to assume that the flow that's induced in the droplet is quite slow, so that viscosity dominates inertia. So we'll visit these assumptions again in a second, but that's a very reasonable assumption to make. We're going to assume that gravity effects aren't important. So you can do an equivalent problem in which gravity is important, but we won't look at that here. And finally, we're going to assume, as I said, that the solute remains dilute. There's no interaction between the flow and the solute. The problems decouple in this model. Great. So bearing in mind those assumptions and doing a sensible non-dimensionalization yields a thin film model that looks like this. So these first two are sort of your classic lubrication equation just by reducing the Navier-Stokes. And the final equation here on the top line is essentially determining the droplet profile, assuming surface tension is the dominant effect. We're going to apply some natural boundary conditions, so some symmetry at the center of the droplet, and then we're going to assume that the droplet height vanishes at the contact line and that there's no liquid going through the contact line. So that's what we've written down here. And In the model that I've written down here, this is the capillary number. So you can see that it's essentially an enhanced capillary number here due to the thinness of the drop. And this TF is the final sort of the extinction time of the droplet. So once we hit TF, there's no liquid left. So our next step is to think about this droplet capillary number in a little bit more detail. So it transpires that for a wide variety of real-world problems, the capillary number is often small. So I'm going to illustrate this with a particular example. So this is taken from Hugh and Larson, who did some experiments and some analysis in 2002. They were looking at the effect of the contact angle on evaporation. But for a particular example of a water droplet evaporating on glass with these parameters for the radius and volume, we're getting capillary numbers on the order of 10 to the minus 7, which is tiny. And this is much more general than this. You can look at a variety of experiments looking at evaporation and the coffee ring effect, and this is a very common thing to see, that the capillary number is small. You'll also see that the evaporation induced velocity here, U star, is also very small. So we made that assumption of slow flow a few slides ago, and that was a very reasonable assumption to make as well. So the important thing is we're going to now think about a small capillary number limit of the flow model we wrote down, which allows us to write down these simple expressions for the free surface, the pressure, and the radial velocity. You'll see that the free surface just decreases linearly, and that the radial velocity depends upon the evaporative flux through this term here. So we could go away and do some more analysis on what happens to the solute, to the coffee inside the drop, but let's zoom in on one particular evaporation model to really illustrate the structure that comes out. So the one we're going to think about is a vapor diffusion limited model. So this is not diffusion of the solute, this is diffusion of the vapor into the surrounding air. So you can go away and write down a problem for how things diffuse away. Essentially, it's a Laplace problem with a mixed boundary value problem on the substrate. You can solve that using some classical techniques, and you'll find an evaporative flux that looks like this. So you've got this inverse square root form of the evaporative flux, and that's coming from that mixed boundary value problem. And if you substitute that into the radial velocity, you get it cropping up in the velocity too. So there's a singularity in the radial velocity, so there's things being moved very quickly to the contact line. So for this particular evaporation model, now we've written down the flow model completely. And so we can now just investigate in detail what happens to the solute because of it. So we do that overleaf. So this is the solute problem. So I've introduced this M at the start here. This is the solute mass per unit area because phi is the concentration and H is the droplet thickness. And this must satisfy an advection diffusion equation. So there is a term here that says the solute mass is being advected to the boundary. And there's this competing term here, which is the diffusion of the mass back away from the contact line where the concentration is quite high. We've written down some sensible boundary conditions to go along with this. So I've got a symmetry condition at the center of the droplet. I'm saying that there can be no flux of solute through the contact line, which of course makes sense. And there is an initial profile based on those forms of phi and H initially that we chose. In the problem, this parameter PE is the thing that determines how strong advection is to how strong diffusion is, and so we have this solutal Peclet number. And the important part of our asymptotic analysis that we're going to see here is that this is typically large for a lot of problems. So if we think back to that Hugh and Larson experiment that I was talking about a minute ago of water evaporating on glass, and I put some solute particles that have radii varying from the colloidal limit to something that's as small as a sugar molecule, then we're talking about Peclet numbers that vary on the small side from 3 all the way up to 5 times 10 to the 4. And we're thinking more towards this end of the spectrum of our regime of interest. And so you can see that the Peclet number is very large. And so we're going to be thinking about this equation in the large Peclet number limit. And so you can sort of see from the off, if the Peclet number is large, we're going to be able to ignore diffusion, but eventually this term is going to be competing with this term, and we're going to have some form of balance in the boundary layer. Okay, so let's have a look at that in more detail. So the naive thing to do is just to go and expand, say the Peclet number is large, do an expansion, and then we're just left with this advection equation, which says that this is the velocity that advects the mass to the contact line. You go and solve that. It's a relatively simple exercise in characteristics, and you get a solution that looks like this. And in particular, if you're interested in this thing from the model, you can say that, well, this tells me how much solute is being advected into the contact line as a function of time, which you can get by integrating this times the velocity at the contact line. And you get this expression, which has been derived previously by Deegan and Popov and other authors for these axisymmetric droplet problems. So this is how much mass is getting into the contact line in time t. So I guess the question is, what's happening to that mass in the boundary layer? So local to the boundary, as I said, there's going to be a competition between the diffusive term and the velocity advecting stuff in. So when r minus, 1 minus r is on the order of 1 over the Peclet number squared, and the mass is on the order of Peclet number squared, we get a balance in the problem which brings diffusion and advection together. So we've got both of these physical effects in our model. And we've essentially reduced the leading order problem to solving this differential equation subject to a no flux condition, which has a relatively simple solution involving sort of an r times an exponential to the minus root r term, and this f of t, which is an unknown that we have to determine. So you could go away and determine f of t in several different ways. You could go to higher order in this analysis and do some matching, but a more natural thing to do is to say, okay, conservation of solute must be true. The solute is not evaporating, it's not getting out of the droplet, so it must be conserved as the droplet evaporates. And so that's what this expression says here. So what I can do is I can take my inner and outer solutions and plug them into this first integral to get an approximation of this left-hand side, evaluate it with the right-hand side, and this will allow me to rearrange and solve for f of t. And the details are relatively straightforward. And you can see that the coefficient of that inner solution depends upon the total amount of stuff that was advected in. So this is my m hat of t. And this is just some coefficient that depends upon the explicit form of the velocity for this evaporative model. Okay, great. So now we've got our inner solution. All we need to do is add it to the outer solution that we found previously, and then we can write down a composite solution that should be valid to leading order everywhere in the drop. So this is the solution we got from the outer advection problem, and here's the solution from our diffusive boundary layer, which, given their explicit functional forms, is this. And if we just for a second zoom in on this inner solution, we can say, hang on a minute, this looks quite familiar. I've got something that looks like an x outside the exponential and a root x in the exponential. And it turns out we can write this as a gamma distribution, so a PDF of a gamma distribution with these coefficients. And that means that the inner solution, even in this dilute stage of the evaporation process, is giving us something that looks like this. So the classical gamma slope that goes up to a peak and comes down to 0 at the contact line. So even at this dilute stage of the evaporative process, we're getting the classical coffee ring peak shape, which is very encouraging. So having made all these predictions and it said that we're getting this nascent coffee ring to form, we would like to know how well our asymptotics capture the large Peclet number limit. And to do that, we are going to compare these asymptotic results to the numerical simulations that we've done of the full advection diffusion equation. So basically, we've coded it up, we've discretized, and we've clustered the grid points in the boundary layer where all the action is, and let it go in ODE 15S. And so here is an example set of comparisons. So this is for the Peclet number being 100. On the left-hand side, we're seeing the profiles in the droplet bulk, while on the right-hand side, you're seeing a close-up of what's happening close to the contact line. So as t increases, you can see that the profiles slowly decrease, and you get this spike near the contact line where the nascent coffee ring is forming. And you can see that in detail in the right-hand plot, where you get this classic gamma distribution profile where it comes in to a peak and then goes down again towards the boundary. And perhaps the most important takeaway from this picture is how well the asymptotics are capturing the numerical results. So the blue lines are underneath these red dashed lines here. We're getting a very, very good comparison between the two. And I think the maximum relative error, if you go and investigate, is on the order of only a few percent in the concentration. So that's really good accuracy for our asymptotic predictions. So now we know that they're reliable, we can use these asymptotics to predict certain properties of this nascent coffee ring that has formed. So for example, we might be interested in the height. So this is the maximum peak of the coffee ring. So in this little schematic here, it's this height here. We also like to know where that peak is. So this is our max. So that's that location here. And then this last thing is sort of a measure of the width of the coffee ring. So it's full width at half maximum, and we call it W1 half. And you can solve for all of these things from the asymptotic solution explicitly. And then we can say, okay, great. So firstly, let's plot them to see what these look like, and secondly, how well is this comparing to the numerical results? And that's what we do on the next slide. So in the 3 plots, so I've got the peak, I've got the location of the peak, and I've got the full width at half maximum. And in each figure, the coloured lines represent numerical results, while the dashed black line are the asymptotic predictions I wrote over leaf. And you can see in every single one, we're capturing it really well, really quickly. And it certainly gets better as the Peclet number gets larger, but it even does an excellent job for Peclet numbers as small as 50 here. So we've got a really reliable way of capturing the essence of this nascent coffee ring. So all of this analysis has been for one particular evaporative flux. And of course, there are myriad different evaporative models you could write down. So it makes sense to have another look at this with another commonly used evaporative model. And one we've chosen to have a look at here is the kinetic evaporation. So this sort of happens when essentially if you put a droplet in a room full of its own vapor, you're going to get kinetic dominated evaporation. Or diffusion happens so quickly that it's the vapor phase that's it's the liquid phase that's limiting the evaporative process. And so you can write down more complicated models than this, but for a thin drop, that means that the evaporative flux is approximately constant across the whole drop, and this is a reasonable model to write down. So going back to the velocity profile and plugging this in, we can find that this is the velocity profile we get in the kinetic evaporation model. And you can see, quite importantly, this is very different to the diffusive one in that it's not singular anywhere. So this changes everything in terms of the boundary layer scaling. So before, if you remember the diffusive model, this looked like p to the -2, and this looked like p squared. Now we've reduced both of those by 1 order of magnitude, or increased accordingly for the m. And that's entirely because this function is now non-singular. So we're actually getting a larger boundary layer here. Diffusion is happening over a larger scale. But the maximum height we're going to see within the boundary layer is smaller. So if you go through all the analysis we spoke about before with the inner and outer solutions, we get something that looks like this. So the first term here is the outer solution. Sorry, there's a lot of text on here, but this is the outer solution, the one that comes from advection. But the remaining terms are the first 3 inner solutions. So you actually have to go to 3 orders in the asymptotic analysis to write something that's consistent for a composite solution. And it's quite a mess, so you can see why I didn't present this one in detail. But you end up with 3 parameters that you can determine explicitly from conservation of solute. And then you've got your composite solution, and you can check how it does against the numerics. So here's a picture of that. We've again chosen the Peclet number to be 100, and you see a very similar style of thing happening, except here the sort of maximum coffee ring height is much lower. And you may not remember, but the scale is also so that the ring itself is a bit wider. So how does the asymptotic analysis do here? So it's not as good as the diffusive case. You can sort of see there's slightly more deviation, but certainly as the droplet evaporates, it gets much, much better. And if you increase the Peclet number, these differences become much smaller. So here we're talking like maximum relative errors on the order of 6-7%, and then reducing down to 1-2% later on. But if you increase the Peclet number to 1,000, you're getting below 5% accuracy for all t basically. So you're getting very good accuracy. And so again, we can also have a look at the properties of the nascent coffee ring, which I've done for 3 different Peclet numbers here, covering 2 orders of magnitude. And you can see again, certainly for the larger Peclet numbers, we do a good job of capturing the numerical results. So same idea before, the dashed lines are the asymptotics and the coloured lines are the numerics. For Peclet number equals 100, it takes a while to get there, but we eventually do converge on the asymptotic solution here. So we are doing a reasonable job again of capturing the solution for the kinetic regime. So, okay, I sort of demonstrated that this process works for the diffusive model and the kinetic model. And you can actually extend this to any evaporative model that you like. But I guess the question we want to go back to is, well, we did all of this assuming that jamming doesn't happen. So maybe we should check when this assumption is no longer valid. So the final thing I want to think about is, when does it all go wrong? So given that we've shown that the asymptotics do a reasonable to very good job of capturing the numerics, we're going to say, let's take the asymptotic solution, track the concentration at its maximum, which is always going to be at the contact line, and see when that sort of hits a critical value at which we might have to consider finite particle size effects, whether that be jamming models, whether that be some form of suspension model. So that threshold is dependent on whatever solute we have in there, so the size of the particles, and also how much we had initially. So we're going to look at sort of various thresholds and sort of have a discussion about what's going on. This is the approximation we're using for that maximum value based on the leading order in a solution. And we'll have a look overleaf at how these do. So on the left, I'm looking at the kinetic flux. So this was the constant evaporation model. And on the right, we've got the diffusive flux. So let's have a look at the left-hand side first. So in here, the red dashed lines indicate 5 different threshold values of the concentration where things might break down, going from 10 up to 10 to the 5. The black lines going from right to left are increasing Peclet numbers, so increasing values of this expression, values of this expression as the Peclet number increases. And you can sort of see that as the Peclet number increases, that we hit each threshold value sooner. So in here, so if we zoom in and look on some numbers, so in the case when the Peclet number is 10, so if we wanted to get up to a concentration of 10 to the 5, we'd actually still be in the dilute regime after 95% of the drying time, which is a huge window of validity for the dilute model. So we'd be missing all of this if we jumped straight to a jamming problem. On the other hand, if we let P be 10 to the 3, and we're looking at something where we only need to get to a concentration of 10, then we're only actually in the dilute window for 3% of the drying time. So in that case, so our dilute model is only valid for a very short period, and we'd have to consider finite particle size effects very quickly. On the other side of the coin, for the diffusive flux, because of the stronger singularity and therefore the quicker growing boundary layer and the faster velocity in the droplet, things break down a lot sooner. So let's look at the weakest case first. So this is P equals 10. So we're right on the cusp of a large Peclet number regime. So if we wanted to get to 10 to the 5, we're lasting 80% of the drying time, which is still pretty reasonable and quite nice that our model is valid for that long. But if we decrease the threshold concentration all the way down to 10, then suddenly we're only valid for 10% of the drying time. And then this just gets worse if you increase the Peclet number. When I say it gets worse, it just means that the dilute regime lasts for a very, very small window, and then we have to start thinking about finite particle size effects. So certainly for the diffusive flux, we need to think about jamming a lot sooner if the Peclet number is more than moderate. So if it's more than, say, 10, 20, we need to start thinking about jamming quite quickly. Whereas in the kinetic model, we learn a lot more from the dilute model. We're getting a lot more information from this stage where advection and diffusion are competing. Yeah, there's a lot more there's a larger window over which we can learn things. Okay, great. So I think just to summarize, what we've looked at in this talk is how solute diffusion can lead to the formation of the nascent coffee ring when a droplet evaporates. So we're getting all of these properties of a peak near the boundary, driven by advection, that's happening much earlier than the jamming regime kicks in. We've shown that this matched asymptotic model can predict the size and thickness of the boundary layer for different evaporative fluxes, and we've compared 2 particular cases, the diffusion model and the kinetic evaporation model. And we've also used our results to investigate certain properties of the nascent coffee ring and shown that they're in excellent agreement throughout with the numerical results that we have. So there's lots that we could be doing going forward, sort of thinking of different shaped droplets or perhaps different evaporation models, but that's work to do in the future. And it's quite interesting to see how far we can let this dilute model go. So just want to say thank you very much for listening. So if you had any questions or want to learn more, please feel free to send me an email or send me a message on Twitter. So there are my 2 contact details. And hopefully the preprint for this work should appear on arXiv within the next week or 2. So if you have any questions, I'd be delighted to hear from you. But otherwise, thank you very much for listening and enjoy your virtual APS.